In the last video, we were introduced to the kinetic particle theory, and based on how the particles were behaving in a solid, liquid and gas, we can use it to predict certain properties of the three states of matter. In this video, we're going to continue to use the theory, but to examine the change from one state to another. So let us first look at the names given to the processes that accompanies the changes in state. For example, when a solid changes to a liquid, we call that melting. When a liquid changes into a solid, we call that freezing. When a liquid changes into a gas, we can either call that evaporation, or we can call that boiling. And when a gas changes back to a liquid, we call that condensation. And the last one may be new, which is conversion from a solid to a gas. We call that sublimation. Alright, so there are certain solids that upon heating they do not melt, but rather they are converted into a gas immediately. Alright, there are three solids that we need to learn in the syllabus. The first of which is solid carbon dioxide, okay, for which we call it by the common name dry ice. So if you were to heat solid carbon dioxide, it changes into the gaseous form immediately without going through a liquid form. Okay, that is also why we call it dry ice, because it is never wet, it's never in liquid state. So therefore we call it dry ice. The second solid that we need to know that can undergo sublimation is solid iodine. And then lastly would be ammonium chloride. So these are the three solids in the syllabus that we need to remember will sublime. Okay, sublime is the verb for sublimation. Okay, solids that undergo sublimation, we say that they can sublime. Now let us examine a scenario where we are heating a beaker of ice. Okay, a beaker of ice from a temperature of -5 degrees Celsius to +5 degrees Celsius. Alright, and we monitor the change in temperature of the substance with time. So at the start, the temperature of the substance is -5 degrees Celsius. This is before we apply the heat. Now, once we start to apply the heat, the temperature of the substance will increase. And at a certain time, the temperature will start to remain constant, and then it will start to rise again. Okay, so this is the graph that we will get if we heat a sample of ice from -5 to +5 degrees Celsius. The graph that we get is called a heating curve, because this is what we obtain, or this curve is obtained by heating a substance. Now there are three very important points to remember about a heating curve. The first important point is this: there is a section, there's a period of time where the temperature remains constant. When the temperature remains constant during heating, when the temperature of a substance remains constant on heating, it means that a change of state is happening. Alright, I repeat, if the temperature of the substance remains constant when heat is applied, it means that a change in state is happening. So if we look at the heating curve that we have drawn, the change of state that we are looking at is a change in state from a solid to a liquid. So we are looking at the process of melting here. So therefore the temperature that corresponds to this particular temperature would be the melting point of the substance. In this case it is water, so it's 0 degrees Celsius. The second important thing that we need to take note about a heating curve is the state in which the matter exists in for the different parts of the heating curve. For example, from A to B, from B to C, and from C to D. What state is the substance found in? If we examine the scenario, we are heating ice from -5 to +5. So A to B, ice is actually in solid state. B to C, melting has occurred. So we are looking at a mixture of solid and liquid. And when the temperature starts rising again at C, it tells you that melting has completed. So from C to D, we are looking at water in liquid state. So that's the second important thing, which is to know what state the substance is in the different sections of the graph. And the last important thing that we need to learn about a heating curve is this, is the explanation for why the temperature remains constant during melting or during a state change. For that, we need to realize one thing, which is when we are heating a substance, we are supplying energy. We are putting energy into the substance. Okay? And normally, the energy will cause a rise in temperature. But in this case, the temperature has remained constant. So imagine a scenario if I were to give you money, but your bank account remains constant. So what must be happening? It means that you must have spent the money elsewhere. So same thing in this scenario, we are supplying energy, but the temperature remains constant, means that the energy is being used to do something. Okay, it's being used up to do something. What is it being used up for? For that, we need to look at how the particles are arranged in a solid. So solid, very closely packed, attraction is very strong. In a liquid, the particles are in a disorderly arrangement and the attraction is not as strong as before. So to convert a solid to a liquid, we need to overcome the attractive forces between the particles. And to overcome attraction, to overcome attractive forces, it requires energy. So what is happening here is that the heat that we supply is used up to overcome the attractive forces between particles to convert the substance from a solid to a liquid. Now let us very quickly look at a very similar scenario. Now we are heating water. Okay, once again we are heating water from 95 degrees Celsius to 105 degrees Celsius, assuming that we can keep the water vapor from escaping and continue to measure the temperature. So let's very quickly construct the heating curve. At the start, it will be 95 degrees Celsius. Similarly, upon heating, the temperature will rise. It will remain constant for a period of time. Then it will continue to rise until it reaches 105 degrees Celsius. Okay, let's go through the same three important points. First point is where the temperature remains constant. When the temperature remains constant during heating, it means that a change in state is occurring. And the change in state that we're looking at here is boiling. Okay, so the temperature that corresponds to this part would be the boiling point of the liquid. In this case, it's water, so it's 100 degrees Celsius. The second important thing is to be able to recognize the state that the substance is in the different parts of the curve. So A to B, B to C, C to D. A to B, we are looking at water in liquid state. B to C is undergoing boiling, so we have a mixture of liquid and gas. And C to D, the water has completely has finished boiling, so now it is entirely in gaseous state. Something that I forgot to do in the last slide, if you are using symbols to represent solid, liquid and gas, do write a legend to make your diagram clearer. Now the last important thing that we need to take note for a heating curve is why the temperature remains constant during change in state, in this case during boiling. So the reason is the same, almost exactly the same. We are supplying heat, but temperature remains constant, means the energy is being used to do something else. What is it being used to? Let's examine the particles in a liquid. It's in a disordered but closely packed manner, but in a gas, the particles are very far apart. So to convert a liquid into a gas, again, we need to overcome the attractive forces. And overcoming attractive forces requires or uses up energy. So the explanation is the same as before. Now this is a recommended explanation as to why temperature remains constant during melting and boiling. So once again, during melting and boiling, the energy supplied is used up to overcome the forces of attraction between the particles to move them further apart, to convert them from a solid to a liquid in the case of melting, or liquid to gas in the case of boiling. Now let us look at a third scenario, which is slightly different. Instead of heating, now we put water in a freezer. Okay, we put it in a freezer and we cool it down from +5 degrees Celsius to -5 degrees Celsius. So if we were to monitor the temperature change with time, this is what we will see. At the start, it is +5 degrees Celsius. As we are cooling down the water, the temperature will drop. At some point in time, it will remain constant, and then it will continue to drop again, right, until it reaches -5 degrees Celsius. Okay, the graph that we get in this case is called a cooling curve, because we get it by cooling a substance down. Now the same 3 points that applies to a heating curve would apply to a cooling curve. What are the 3 points? First, the part where temperature remains constant. If temperature of a substance remains constant when we are cooling it down, it means that a state change is happening. And in this case, we are changing the substance from liquid to solid. So the change in state that we are seeing is called freezing. So the temperature at this point would correspond to the freezing point. In this case, we are looking at water, so it's 0 degrees again. The second important point would be the state the substance is in at various parts of the cooling curve. So from A to B, we are cooling down the liquid, we are cooling down water in liquid state. B to C, freezing is occurring, so we have a mixture of liquid and solid. And C to D, the water has already frozen, so you get solid state. Once again, it will be good for you to have a legend to tell us what S, L, and G mean. And the last important point is the same. The last important point, why does temperature remain constant during freezing or when we cool down a substance? At certain points when we cool down a substance. Now it's very tempting to use the same explanation as before, but think about it, the situation is completely different. Previously we were heating a substance, so we are supplying heat. In this case, we are cooling down a system, so we are removing heat. Right? When we cool down a substance, we are removing energy from it. And when we remove energy from a substance, by right, the temperature will drop. So in this case, it has remained constant. So imagine if I'm taking money from you, but somehow your bank account remains constant. What does it mean? It means that you are earning your own money. You are producing money on your own. So in this case, since the temperature remains constant, it means that the substance is producing energy on its own. So how is it producing energy? Again, let's take a look. In liquid state, the particles are in a disordered manner, but in a solid state, the particles are in an orderly manner. So for that to happen, they need to form forces of attraction. okay, from a liquid to a solid, forces of attraction are formed, and the forming of forces of attraction will actually release energy. Okay, so the system is making energy on its own, so even though we are removing energy from it, it's creating its own, so temperature remains constant. Again, this is the recommended explanation. During freezing or condensation, energy is released as the particles move closer and form stronger forces of attraction. Now, this is a typical question that we will get for kinetic particle theory, where we are supposed to construct a heating or cooling curve based on the information given in the question. So let's try it together. In this case, substance A with the following melting point and boiling point is cooled from one temperature to another and then heated to another temperature. Alright, so we are supposed to draw or sketch how the temperature changes with time, and to identify for each section what state substance A is found in. Now, for such a question, it may seem easy, but it's very prone for students to make mistakes as well. So there is a recommended way for you to approach this question, and let's try to do it together with me. Okay, so the first step is to draw, of course, the x and y axis. The y axis is temperature, the x axis is time. Now the next step is very important. The next step is to plot on the y axis all the temperature values that appears in the question. For example, there is 110, okay, there is a 98, there is a 25, and then a -10, and then a -15. So step number 2, which is also the most important, is to write in or plot all the temperature values onto the y-axis first. The next step is to locate the boiling point and melting point of the substance and draw a dotted line across the x-axis. Okay, why? It's because it's to remind us that this is the part where a change of state would occur, meaning whenever the temperature hits or meets this line, it has to remain constant for some time because a change in state is occurring. And once you have done with that, we can go on to plot the graph very easily. So first, substance A is cooled from 25 degrees Celsius to -15. So when it goes down, does it go down straight to -15? Answer is no, because it encounters the freezing point. So it will remain constant for some time before it goes to -15. And then it's heated up to 110 degrees Celsius. So again, temperature will rise. But does it rise straight to 110? Again, no, because it hits the melting point. So it remains constant for some time, goes up to the boiling point, again remains constant for some time, and then it goes up to 110, the final temperature. Okay, so I hope that you can see with the boiling point and melting points put in, it becomes very easy to sketch the graph. Now the last part would be to write in the state in which substance A is in for the different parts of the graph. From 25 to -10 is actually a liquid, and then freezing occurs, so liquid to solid, solid, liquid plus solid. From -10 to 98 is liquid, liquid plus gas, and then gas. Okay, so if you follow the steps shown in this question, you will find that drawing the heating and cooling curve for the scenario described in the question becomes very straightforward, and you are less likely to make mistakes by following the steps. Next, I would like to introduce the concept of a number line in kinetic particle theory. Now it's very useful, especially for questions that are very complicated. In this example, we'll use it on a simple one. So which substance is a solid at 20 degrees Celsius? Some of y'all may be able to see the answer directly already. Okay, but for some of y'all, you may find it harder, and that's where the number line is going to help you. What is a number line? A number line is like this. We draw a line, okay, of increasing temperature from left to right. Okay, so as we move from left to right, the temperature increases. Next, I want you to draw 2 points on the number line. The lower point represents your melting point, and your higher point represents your boiling point. Okay, so the next thing is to recognize that at temperatures below your melting point, the substance exists in a solid state. Between melting and boiling point, the substance exists as the liquid state, and above boiling point, the substance exists as a gas. Alright, so let's see how we can apply this. This is the number line that I was talking about. So let's see how we can apply this number line to this question. So the question wants a substance to be a solid at 20 degrees Celsius. So we are looking at a solid, and for it to be a solid at 20 degrees Celsius, 20 must fall within the region of a solid. So from the number line, I hope you can see very clearly now. For a substance to be a solid at 20 degrees Celsius, the melting point must be more than 20 degrees Celsius. So in this case, the answer is clearly D. Now let me change the question slightly. So if I'm asking you which one is a gas, okay, which one is a gas at 70 degrees Celsius? Okay, so in order for something to be a gas at 70 degrees Celsius, 70 must fall within the region of a gas, and that means that the boiling point must be lower than 70 degrees Celsius. Okay, so if we look at the options given again, there's only one substance for which the boiling point is lower than 70. So in this case, in the modified question, the answer is B. Now in this last part, we are going to look at the difference between boiling and evaporation. Previously we saw that when a substance changes from liquid to a gas, we can either call it boiling or evaporation. But do they exactly mean the same thing? The answer is no. Alright, so we're going to examine the differences between evaporation and boiling for 4 different areas. So firstly, let us look at the temperature at which boiling or evaporation occurs. We have learned that boiling takes place, for example water, boiling takes place at 100 degrees Celsius, so it occurs at a fixed temperature. Alright, however, for evaporation, does it take place at only one temperature? Answer is no. If it only takes place at one temperature, then your clothes wouldn't dry on a sunny day. Okay, so evaporation takes place at any or at all temperatures. Okay, if you have ever boiled water before, you will notice that when it's boiling, the bubbles appear from all parts of the liquid. So boiling occurs throughout the liquid, whereas evaporation, we have learned in primary school that if we accidentally spill water and we want it to dry up faster, we can actually spread out to increase the surface area. Now why is that so? Because evaporation occurs only at the surface of the liquid. Next, if we observe how fast boiling occurs versus evaporation, you will know that evaporation is a slow process. That's why your clothes take a long time to dry. Whereas boiling, if you boil water, if you leave it unattended for some time, you'll find that all your water will be gone. Alright, so boiling is a fast process, whereas evaporation is a slow process. Now, temperature change, we have looked at a heating curve, and we have seen that the temperature remains constant during boiling. However, for evaporation, temperature of the substance will decrease. That is why our body cools down when our sweat evaporates. So is there a contradiction here? Because I've already mentioned, we have seen that when we change from a liquid to a gas, we need to overcome the attractive forces between the particles, and that requires energy. That takes energy from the substance. So why would the temperature remain constant? Shouldn't it drop in both cases? The important thing here is to remember that for boiling, we are supplying heat constantly. Alright, so that is why the temperature, instead of dropping, but we are supplying heat continuously, so the temperature remains constant. So there's no contradiction here, just that for evaporation we are not constantly supplying heat, but for boiling we are constantly supplying heat.